Hello everyone, my name is Karan Saxena and I'm from Windsor, Ontario.
And I'm Arman Tashti from Calgary, Alberta.
Together, we'll briefly demonstrate the main features of OpenNTF, our library to benchmark neural models for forming collaborative teams. OpenNTF is a Python-based library for neural team formation where we want to form a group of people that hold a collective skill set which is required to solve a particular task. Team formation is a subfield of social information retrieval where the right group of experts is more important than forming a right group of collective documents. OpenNTF's main goal is to provide fast, fair, scalable and reproducible framework where a reproducible benchmark platform for neural team formation. Well, out of the box, it has Bayesian and non-Bayesian neural models. OpenNTF is also tested on 3 large-scale datasets from computer science publications from DBLP, movies from IMDb, and patents from USPT. As an important part of OpenNTF, we have included negative sampling methods that can be easily used during the model training to boost speed and increase inference accuracy at test. Now we'll show you how to set up, install, and execute and evaluate the results from OpenNTF. Now I will head over to the notebook where we have executed all the commands in the interest of time. And so OpenNTF requires Python 3.8, PyTorch, and some other libraries that are needed for its execution. Here we'll be installing, setting up our environment and Python 3.8. followed by the cloning of GitHub repo of OpenNTF, and then we'll be installing all the libraries that are mentioned in requirements.txt file. After doing this, you can see the folder structure that has been created. Now I'll go ahead and explain you a couple of folders in this directory. The first folder is data, having raw and preprocessed folders. Raw is the folder where raw files of a dataset will be stored at, and unprocessed files. Preprocessed folder is the file where we'll be storing our sparse matrix pickle files that can be readily fed into the model training phase. Output is the folder where we'll be storing all the saved models, evaluation metrics, and results. Source is the folder where all the magic happens, consisting of different folders for different needs. For example, the common folder having all the class definitions that are being used in our project. This is the team inheritance hierarchy diagram where we're using team as the parent class for all the subchild classes. Followed by the evaluation folder having metric.py consisting of metrics to evaluate from. Followed by the model folder having all the different model files which are being used in the architecture. If you want to see the model inheritance diagram, it's here where we are leveraging PyTorch NNL module class for all the different models that we have implemented in the package. Now, if we go ahead and want to see the default hyperparameters that are being there, that are there in the package, we can just use cat param.py and see all the different hyperparameters that are being used. Main.py is the main driver class which executes all of this. Out of the box, we have set negative sampling to off, or as in none by default, but depending upon the use case, we can always select from the 3 available options, which are uniform, unigram, and unigram at mini batch. Next, we will be demonstrating how to execute the package, make any changes necessary to param.py using this command or using your preferred text editor, and evaluation of results. For that, I'll hand it over to Arman. Thank you.
Thank you, Karen. I'll elaborate on the hyperparameter before running the model. So we can choose the hyperparameters for feed-forward neural network and Bayesian neural networks here. L means the number of nodes in each layer and number of layers. Basically, we pass a list of numbers indicating the number of nodes in each hidden layer. LR is the learning rate. B is the number of instances in each mini batch. E is the number of epochs. More importantly, number of N and S means the number of negative samples that we want to use if we are using negative sampling heuristics as our objective function. And NS means negative sampling, and we choose the type of negative sampling we want. Uniform negative sampling draws experts from a uniform distribution with the same probability for each expert. Unigram negative sampling draws the experts using the frequency of experts in all of the teams. And unigram underline B uses the frequency of experts in each training mini batch. And for Bayesian neural networks, we have another hyperparameter called S, which is the number of samples. As you may know, Bayesian neural networks learn a Gaussian distribution of weights instead of just learning weights. So when we want to infer new teams, we need to sample from that distribution. And by default, we choose to sample one set of weights for inference. Also, we've implemented two different types of input skills for our neural models. So we can use either sparse vectors or embeddings as input variables, and we create the input embeddings using inspired by Hay and Mikolov, and using the doc2vec package from Gensim. Here you can choose the number of nodes in the embeddings using the D, number of epochs, the type of training algorithm, which can be either distributed memory or distributed bag of boards, and finally the size of the window. We can also choose whether we want to train the model, test, evaluate, and plot the results or not. Moreover, we can choose a number of folds for our k-fold cross-validation, and the initial train test split, which will take 85% of the data for training and validation, and the remaining 15% for test set. Finally, we can also remove outliers using the filter hyperparameters here. Mean underline NT means that we want to remove any expert that has been in less than 75 teams. And mean team size means that we want to remove the teams that have less than 3 members. Finally, we've implemented parallel pre-processing of the raw data, which has increased the speed by 2.5 times, as you can see in this plot, at least. Depending on your compute power, you can have more code and definitely have a better speed boost. And our package delivers a one-click command that can run several models, as you can see here, on several data sets and domains. Here we've showcased 2 different data sets and 5 different models. And again, in interest of time, we've already run the training, but you can see the list of the models using this command and in the output folder. Finally, if you look at our directory structure, we name the folders using the hyperparameters for each model. So here we have used, here you can see the saved models after each epoch for each fold, and also the prediction of our models for each fold, and moreover the evaluation metrics and the image for ROC metric. Here we've shown the ROC for one of the models that we've trained. As you can see, because the data was a sample toy dataset with only 31 samples, the model is not performing really well, but it's not a surprise for us. And finally, here we have the metrics, both ranking and classification metrics that we save in a Panda data frame in the formats of CSV. So we have precision, recall, NDCG, and map at 2, 5, and 10. And also at the end, the AUC, which is the area under the ROC curve. Just to reiterate our features, we have implemented parallel pre-processing that speeds up the generation of the sparse metrics. We split the dataset first to training and test sets, and then use k-fold cross-validation for training and validation. We utilized NN module from PyTorch to create our parent neural transformation class called NTF, which consists of training, test, and evaluation. On top of that, we've created feed-forward and Bayesian neural networks, which are inherited from NTF. You can also extend our package by inheriting a class from NTF and creating your own neural network. Again, we've also implemented 3 different negative sampling heuristics that increases efficiency of training and also effectiveness at inference. And with that, I thank you for the time you spent for listening to us.
Thank you so much, everyone. And here's a quick glance at the results section that are being used on the different dataset. Thank you for your time.